Okay, welcome everyone. My name is Bethany Ellman. I'm professor of planetary science here in this division, geological and planetary sciences at Caltech. I also have the pleasure of being the associate director of the Keck Institute for Space Studies. I want to welcome those of you on the room, those of you online, to one of our monthly series of lectures. To those who are outside and we tore you away from the buffet table, it is worth it because we've got an outstanding speaker today. So, for those of you who might be unfamiliar, KISS, the Keck Institute for Space Studies, exists to basically revolutionize the way we explore space and we do measurements from space. So we seek outstanding science and technical development work in astronomy, earth sciences, planetary sciences, all toward furthering and improving how we explore and how we learn about our own planet from space. So as part of that, we bring people together from campus, from JPL, through workshops, through technical development, and through our student affiliate program. And I will welcome Niyati Desai to the stage to take it from here in terms of the introduction of our speakers. So enjoy the program today.
Thank you, Professor Ellman. Hi, everybody. Welcome. Thank you to everyone in the audience for coming today, and also to everybody online for joining us to hear The Rhyme and Reason of Juice by Dr. Jeffrey Plaut. Dr. Jeffrey Plaut is a senior research scientist and project scientist at JPL, and he is a co-principal investigator on the RIME experiment on juice and the deputy investigator on its sister instrument, Reason, on JPL's Europa Clipper mission. Interestingly, he actually has a Bachelor of Arts with a concentration in music from Brown University. He then went on to receive a PhD in Earth and Planetary Sciences from Washington University. And finally, he came straight to JPL and has been there for almost 22 years now. During his time there, he has participated in numerous planetary and Earth projects, including Magellan at Venus, the Shuttle Imaging Radars, 2001 Mars Odyssey, Mars Express, and Mars Reconnaissance Orbiter. In 2017, he received the JPL Explorer Award for the 2001 Mars Odyssey's extended mission accomplishments. He's also been a guest on several radio shows, including Planetary Radio, our own KPCC, and The Space Show. A fun fact about him is that he's actually a national ultimate frisbee champion. I'm sure we're all very excited to hear what Dr. Plaut has to say to us today, and so please help me in welcoming him.
Thank you so much for the kind introduction and the kind welcome. Thank you, everybody, for coming out to listen to the talk, and for those of you online as well. I feel right at home here at Caltech in the geology building. So why don't we just get to it, and I'll be advancing the slides. So there are three, I'm going to break the talk down into three pieces here today, so hopefully this will help you keep track of what's going on. So we'll be talking about Jupiter and its icy moons. And in particular, what are the icy moons? Why are they interesting? What do we expect to learn about them? Then I'll go into some detail about this JUICE mission, which is on its way to Jupiter as we speak. And finally, talk to you about the technique that we're going to be using on JUICE with the radar instrument that JPL has contributed to called RIME, and talk also about its sister instrument Reason, which will fly on Europa Clipper. So let's move ahead. Jupiter and its icy moons. So the solar system has two solid, rocky, big planets, Earth and Venus. Let's set those aside for the time being. And think about the next group in that family of solid objects in the solar system. And these are the medium-sized worlds. Now, they're not planets, they're not moons, they're worlds, okay? So don't worry about nomenclature, right? Because if you look at this diagram, Mars is a little bit bigger, but then you have a whole set of objects here, which they're worlds. Ganymede, Titan, Mercury, Callisto. Okay, maybe some of them orbit another object, but some of them orbit the sun, some of them orbit something else. But nevertheless, in size, they're comparable. And also, as you go down around the corner here, you see Io, another of the moons of Jupiter, of the 4 major moons of Jupiter. This is not an icy world, so we're not going to talk about it. Here's a moon we call Moon. I think we're all familiar with that, and it's a good point of reference to think about the sizes and the characteristics of some of these other worlds. And then here's Europa, and then there are some other objects in this same size range down here, also members of the solar system. So yes, some are planets, some are moons, but let's just think about them as worlds and how are worlds put together. So here are the 3 that we're going to talk about. Ganymede is the largest natural satellite in the solar system. Titan looks a little bit bigger in here, but don't forget it has an atmosphere. So we're talking about the size of the solid body. Ganymede is the winner. And then we have Callisto and Europa. So those are the 3 icy moons of Jupiter that are the subject not only of this talk, but also of the study of these spacecraft. So as I think everybody knows, Jupiter is kind of its own little mini solar system, right? If Jupiter were a little bit bigger, it'd actually turn on as a star. So it's got its own set of objects. And these are the 4 major Galilean satellites, or the 4 moons of Jupiter. And you can see in order from inner to outer, we have Io, Europa, Ganymede, and Callisto. So let's look at just a very fundamental property of these objects, which is their density. And there's a lot you can infer from just this very simple single number about one of these worlds. So when we talk about the bulk density of an object, just keep in mind that we usually use water as a reference. Has a value of 1. And basaltic rock, which is a typical rock on the Earth that floors the oceans, for example, has a density of 3. So interestingly, as you go from the innermost of these moons to the outermost, you have higher density to lower density. And you can see that Io is actually more dense than even basaltic rock, and that implies that in its interior, somewhere in its interior, it has more dense material than just rock. And in fact, we believe it has an iron core. By the way, the Earth has a bulk density over 5. So it's kind of off the charts on these guys. But as you go further away from Jupiter, these values drop, and then Europa is actually approximately the same density as basaltic rock. Ganymede and Callisto are down around 2, which is roughly the average of these 2 values. So we might hypothesize that Ganymede and Callisto are made up of 1/2 rocky material and 1/2 material that might have the density of water, for example, ice. And in fact, that's kind of the going explanation for, in particular, Callisto, that it's about 50-50 rock and ice. Now, how is it structured? Is it mixed evenly, or are there layers of rock and ice? Those are the kinds of things we want to learn about these objects. So let's walk through each of these 3, and we'll look at the surface, and we'll look at what we think is going on in the interior of each of the 3. So from the outermost, Callisto, there's some very basic observations. Now, of course, these objects have been visited by several spacecraft. The Voyagers, if you remember, they had flybys of the Jupiter system, but they were targeting those moons, so they got some fantastic images of the moons. And then there was the Galileo spacecraft that orbited Jupiter and had many flybys of many of these moons. So we got some great data from those 2 missions, and that's what you're looking at here. So Callisto, we know, is more or less, here's a global view, it's rather uniform, and there does not seem to be a lot of evidence of mountains or valleys or faults or cracks or anything like that. So little evidence of any kind of tectonics or deformation. Also, it's very heavily cratered. In fact, when you count up the number of craters and you use craters as a measure of the age of a surface, Callisto is as heavily cratered as any object in the solar system that we've ever seen. In contrast, Ganymede, now remember the largest moon, it has a lot of variety to its surface appearance. In particular, it has dark zones and it has lighter zones, and the boundaries between these zones are rather sharp. And this is telling us something about how these form. It doesn't necessarily give you the answer of how they form, but it's telling you something. And also, there are a number of lineations and grooves that may be faults. They probably are cracks. Here's a zoom in on this, the center of this image, and you can see that many of the terrains here have been given names because people have studied and mapped the surface of Ganymede from these spacecraft observations. And there's, in particular, a contrast not only in the brightness between these darker zones and these brighter zones, but actually the lighter terrains seem to have fewer craters, and it suggests that maybe there was some kind of resurfacing, that the darker terrains they're old, not quite as old as Callisto, but dating back to 3 or 4 billion years old, and then these intervening lighter terrains seem to represent a later episode, and they have not accumulated as many craters. So how does an object like this, how does it change its surface? How does it resurface? Those are some of the mysteries we're trying to look at. Europa is sort of its own thing. It's Ganymede, but taken to the next level. There are many terrain types. There's a lot of complex surface morphology, all kinds of intersecting lineations. You can see here a zoom in here. This is a much higher resolution image from Galileo. You see the scale bar down there in the lower right, which says 20 kilometers. So this is a few hundred kilometers across. Some of these blocks that maybe you can pick out here, they seem to have rotated into different positions, and people have taken the images and literally cut them up with scissors and put them back together. In some places, it almost has the appearance of icebergs floating on a sea. So there's a lot of really intriguing sort of evidence that perhaps the ice and liquid water have interacted to generate a lot of the features here. Also, it is very lightly cratered, in great contrast to Callisto, which is very heavily cratered, and Ganymede, which also has a very old cratered surface. Here, when you count up the number of craters, you get an age on the order of 100 million years. Geologically speaking, that's super young for planetary surface. So the mounting evidence for Europa is that there's interactions with liquid water and ice, and it may be ongoing because only 100 million years of craters have accumulated on average. So there may be places that have overturned, or perhaps water has leaked onto the surface and smoothed out terrains or moved these blocks around in very recent times. So what about inside the moons? As you'll see, one of the techniques we're using is what sometimes referred to as ground penetrating radar. So we want to look inside the moons, and then we have all kinds of other tools to determine what might be inside, in particular the different gravitational signatures of the moons, and also how they interact with magnetic fields around Jupiter. Tells us a lot about what's going on in the interior. So here are our three moons, and cutaway models of sort of, this is pretty much the going idea these days of what's inside each of these moons. And these are some very nice illustrations which I stumbled across by someone named Kelvin Ma, and they are consistent with published models, but he's a tremendous graphic artist who has all kinds of cool stuff online, so have a look out for his stuff. So let's start with Callisto. Remember again, the average density of Callisto is like a 50-50 mix of rock and ice. At the surface, it is icy. We have evidence that there's ice right at the surface, but the dark color indicates that it's mixed with rocky material or dust or sand or something. The best models of how the interior evolved say that somewhere below that icy, dirty crust is a liquid layer. And then the bulk of the interior is believed to be some kind of mixture, maybe a simple, even mixture of rock and ice. So what we say about Callisto is that it has not significantly differentiated. That is, it didn't have a global event where material segregated and the heavier material migrated towards the core and the lighter material floated to the surface. Most planets, most worlds that we observe are differentiated. For example, look at Ganymede. The best model of Ganymede is, again, an icy crust, a liquid ocean in the subsurface. Interestingly, another layer of ice, because there are several phases of ice, and as you change the pressure, ice, even if it's at the same temperature, will become stable under that pressure compared to the water adjacent. So it looks like there's some kind of sandwich of ice, liquid, ice again, but then in the interior, clearly Ganymede has a dense interior. In fact, of all these objects, it's the only one that has a magnetic field, which we believe comes from the core, the way the Earth has a magnetic field that is related to motions in its core. So this is a nice, interesting sort of arrangement. When we go to Europa, we have something similar, but again, it's its own thing, which is there's an icy crust, for sure, an icy crust. It's very thin, relatively, compared to these other worlds. We believe that the icy crust of Europa is on the order of 10 kilometers thick. Now, that means it could be 10, or maybe in some places even less than that, or it could be 30 or 40. It's the same order of magnitude, right? So that's a big mystery, a big puzzle, and actually a piece of information we really are eager to learn about Europa is how thick is that icy crust? How deep do you have to go through the ice to get to that liquid ocean? And that liquid ocean, it's calculated to contain more water than all of Earth's oceans combined, because that liquid layer doesn't look very thick, but it's probably 100 kilometers deep. And the Earth's oceans are only a handful of kilometers deep at their deepest. So we're talking about a lot of water, and in both the cases of Ganymede and Europa, there's heat coming from the interior, so that interface at the bottom of the ocean may have a lot of exchange of heat and minerals, and that may provide the energy for microbes the way it does at the bottom of the Earth's oceans in the vicinity of spreading centers. So here are some outstanding questions about these icy moons. What is the interior structure of each moon? I showed you the models, but those are just our best guesses at this point based on the evidence. How thick is that outer ice shell, in particular for Europa and Ganymede, because clearly the surfaces of those two objects are indicative of interactions between that buried or that interior liquid and the outer icy shell. These subsurface oceans are probably salty in some sense. That is, they have dissolved minerals or ions. What is that composition? We know it's primarily liquid water, but what else is in there? So what's dissolved in those oceans? Do the oceans, quote, communicate with the surface? And again, we have good evidence, particularly on Europa and also on Ganymede, that there is some kind of interaction or communication or exchange of material from the liquid layer to the icy layer and possibly even to the surface. And how does this happen? And is it ongoing, or is it only something that's happened in the past? A more general question, why are these three worlds so different? What processes are acting currently to modify their surfaces? What processes have acted in the past? And ultimately, a big question here, because there's water, and we know on the Earth, wherever there's water, there's life, do any of these moons host habitable environments? None of the missions that I'm going to describe to you are life detection missions. It would be quite a jackpot if one of their instruments found some piece of evidence that was convincing evidence that there's life, but that's not what they're designed to do. Really, to find evidence of life, you need to go in and you need to touch the samples. And in some cases, for Mars, for example, we're thinking you actually need to bring them back to Earth to really make a convincing case for life. Nevertheless, we want to understand, could there be life? Is there an environment that might support life? Okay, moving on to the JUICE mission. Oh, 1/3 of the talk, 20 minutes. That's pretty good. Yeah. Okay. JUICE is the Jupiter Icy Moon Explorer. So I'm going to give a little history about how this mission came to be. So 15 years ago, whenever that was, 2008? Here's a very busy slide from a presentation that was given to the Outer Planets Advisory Group, OPAG. Some of you are active members. Anybody? Rosalie, I see. Yeah, okay. And this was a proposed mission that got a lot of traction as a joint collaboration between the European Space Agency and NASA, the Europa Jupiter Science Mission, EJSM, and it consisted of two parts, the NASA-led Jupiter Europa Orbiter and the ESA-led Jupiter Ganymede Orbiter, JEO and JGO, and that's shown in this picture on the left. A couple of spacecraft, one of them's over at Ganymede, one of them's here at Europa, and they're both doing their thing, and they're going to work together, and it's going to be a wonderful global kind of collaboration. Well, it didn't quite work that way. So sometime between 15 years ago and 11 years ago, NASA decided, oh, we're not going to do that after all. We've got other things on our plate. Meanwhile, ESA said, we've got a mission here. We've got the Ganymede orbiter mission, and we're going to do it. So just a few years later, ESA announced, and they even gave it the name JUICE, what was the JGO, Jupiter Ganymede Orbiter, became JUICE. And they announced it was going to happen, and they said, anybody who wants to put an instrument on that, send us a proposal. That's how these things work, right? You have a mission concept, you have some ideas of what kind of measurements it might want to make, but it's up to the scientists and the institutions to present their ideas in a proposal on what should fly on that spacecraft. And so we here at JPL, and I'll get into this a bit later, we had flown some of these radar sounding instruments in orbit around Mars, and they do a great job looking through ice. And we had been thinking actually for many years that we wanted to send ice sounding radars to the Jupiter icy moons. So we got together with the Italians, who are our frequent partners on radar missions or radar instruments in space. And that dates back to the shuttle radar instruments and Marsus and Sharad, which I'll talk about on Mars orbiters. And JPL collaborated with the Italian Space Agency and the scientists in Italy to propose the RIME instrument, which succeeded in getting onto the mission. So that was 11 years ago, and a lot has happened since then, but let's jump ahead to 2 months ago when the mission lifted off from the Kourou Space Center, which is in French Guiana, South America, adjacent to Brazil. And this is the launch site for most of the ESA missions. They launch from here. And this is the Ariane 5 rocket. At the top is the JUICE spacecraft. And this was in mid-April. So we've been in flight for 2 months now. And I'll show you how we get to Jupiter in the next slide. No, I won't show you how. I'll show you in the next slide after that. This is what the suite of scientific instruments that JUICE carries. And I'm not going to go into much detail, but you see it's really loaded with all kinds of different instruments. Down here is the radar sounder we call RIME, down there in the lower left. There's cameras, there's visible and infrared spectrometers, there's an ultraviolet instrument, submillimeter, radio plasma, laser altimeter, magnetometer. That's a very important instrument for understanding what's going on in the interior of these worlds. A particle detector, radio science, radiation monitor. It's got a little bit of everything. It really is. It's I think what we call in NASA a flagship. It's got a ton of instruments, very capable, and they've been contributed by instruments by institutions all over Europe as well as from the US. Oh, Okay, so I've got a little movie here. And hopefully this comes through online with the animation. So this shows just shortly after launch. It's kind of a speeded up artist representation of the different deployments of the different instruments, scientific instruments. And this first one that you see there now sticking out, that's the RIME antenna. And I'll talk some more about that. That thing that just jumped out of the jack-in-the-box there, that's the magnetometer boom. You want to get your magnetometer as far away from the spacecraft as possible so it doesn't get interfered with. And then there are some other probes for radio and plasma wave observations. So I'm going to play it one more time and just watch this sequence of the RIME antenna right here at the beginning. You'll see 6 different steps. 1, 2, 3, 4, 5, 6. Now, I should have known, but when I saw this animation for the first time, they had only put it together recently, about 6 months ago. And I saw, oh, we need 6 things to go right to get this antenna straight. I thought, oh, this is me. There may be some nervous moments here. And sure enough, that is how it turned out. I will say that the antenna was very kindly provided for us. It was not a RIME design. It was given to us by the spacecraft. They went out and procured it, and it works beautifully now that it's out there. But it gave us some anxious moments, which I'll get into. Okay. So how do we get there? So I think most of you are familiar with this concept of gravity assists flybys. This mission has a lot of flybys before it gets on its way to Jupiter. So we had the launch on time here in April. In about a year, we're just cruising along just slightly ahead of the Earth at about 1 Earth distance, 1 AU from the sun. And so about a year later, the spacecraft will come back, and it's doing a very interesting flyby gravity assist where it's timed so that it'll fly by the moon and fly by the Earth and collect some extra energy from both of those flybys on the same day. And that happens in August of next year. About a year after that, we take a left turn and we go in towards Venus, do a Venus flyby, come back to the Earth another year after that. And then finally, that puts us on a wider elliptical orbit. That's this sort of large elliptical orbit that you see there in the middle of that diagram. And then we have the final Earth flyby 2 in 2029. That sends us on our way to Jupiter, and we finally get there in 2031. So it's going to take a while. If you had a powerful enough rocket, you could just go straight to Jupiter from the Earth. But ESA doesn't have that, so their navigators designed this nice method to get us to Jupiter using a minimal amount of fuel. Okay, so we arrive in 2031. Then we spend several years, almost 4 years, flying by the moons of Jupiter multiple times, including Europa, Callisto, and Ganymede. And then finally, we end up in orbit around Ganymede. And that's never been done before. No spacecraft has ever orbited the moon of another planet other than our moon. So there are several firsts. This Earth-Moon flyby gravity assist is a first. The moving from a orbit around one planet to an orbit around its moon is another first, and the first orbiting of another planet's moon. For the flybys, there are a large number of them. Unfortunately, only 2 of Europa, but that'll be covered by someone else, as you'll see later. We do have 12 flybys of Ganymede and 21 of Callisto, and then eventually we get into orbit around Ganymede, and we'll be able to make hundreds of orbits of Ganymede to really study it in detail and do a complete map. So in particular for Ganymede and Callisto, we're going to get some great coverage and some great mapping from this campaign. So 8 more years to get to Jupiter. Once we're there, we're going to do 4 years of science. We'll see if they're able to extend that even longer. Okay, now I'll talk about this technique called radar sounding. Has anybody here ever heard or seen an image or something about Marsus or Charade or anybody? Okay, how about Lake Vostok in Antarctica? Anybody familiar with that? This same technique, radar sounding, is really how it was nailed down that there is a lake under the Antarctic ice sheet near the South Pole, what's now known as Lake Vostok. So what is RIME? RIME is the Radar for Icy Moon Exploration. I think it's a really nifty acronym. It's like it's not tortured. It's like one letter for each word. And it's all in English. Also, it makes a word that is a kind of ice, so it's kind of cool, right? Okay. So how does this work? This is at a very basic level. I'm not going to dwell on this. Very basic. The satellite flies over the terrain. It sends out radio pulses straight down, okay? It's not off to the side. It's straight down, and they bounce off the surface. But some of them, okay, it sends them out at a high rate, okay? 100 per second. So that's like a musical note, right? 100 pulses a second. It's making this humming sound by the number of pulses that it's sending out. But there's time between those pulses to turn off the transmitter, open the receiver, and get the echo, and then close it again and again and again. That's radar, right? Radar is sending out a pulse, waiting for the echo, and recording it. And we do that on these millisecond timescales. Anyway, some of the energy will, in fact, probably most of the energy in just about all cases will be reflected at the surface. But some of it will also be transmitted or penetrate into the subsurface. And it could just go on forever and we never hear from it again. But if there's another boundary in the subsurface, and by boundary I mean a place where there's a layer that has a contrast in its electrical properties with the layer adjacent to it, a particular electrical property known as the dielectric constant, also known as the refractive index. If there is such a boundary in the subsurface, then you get a second echo. So that's what you see here. So if you're thinking about this vertical dimension as time, here you have the surface echo. You wait a little while, then you get another echo from the subsurface. And if you stack all of these echoes together as you go along, you can make an image. And the image is like a cross-section or a slice through the terrain. But the vertical dimension is time. The horizontal dimension is distance. And some examples of where you might have this electrical contrast is if you have ice overlying rock. So you have a slab of ice on top of a rocky surface, for example, the polar ice caps of Mars. Then maybe you'll get an echo. Maybe that radar wave will traverse through the ice, and radar actually is quite happy going through ice. And then when it hits that boundary of the ice with the rock, then it says, oh, wait a minute, I can't penetrate that, or that's a different material, I'm going to reflect some more of my energy back. And that's how you get that second echo. And also, in the case of Lake Vostok, of course, this has been demonstrated. This is with these radars on aircraft that we fly in Greenland and Antarctica. Ice overlying liquid water also provides that very strong contrast, and so you can see that boundary in the subsurface. Just quickly, what does RIME consist of? So a bunch of boxes of electronics. All the shiny ones were built here at JPL. This one that's coated in black paint was provided by Italy, and it includes the digital system, which is kind of the brains of the instrument. And the receiver is actually integrated here on this one. And so we have the receiver, the transmitter, we have these matching networks, which are interfaces between the radar electronics and the antenna, and then the antenna is down here, which you saw that animation of these different legs opening up. I'll just say quickly about how a radar like this works. If you know what analog to digital conversion is, or digital to analog conversion, that's basically what we're doing. We take digital signals, so we have a digital source. We convert them to analog, and then we're working with radio frequency, RF components. They're analog. They're variations in the energy going through wires, but they're not digitally encoded in ones and zeros. And then they get out to this antenna, and you can think of an antenna. Clearly, that's an analog device. It gets out towards the target. The target is not digital. The target is the analog. The echoes. So everything's analog. We receive them. We pull them back in with our receiver, and then it gets to the digital system, and it digitizes them. So you've gone from digital to analog, back to digital, and that allows us then to send them back to the Earth in zeros and ones. So I want to take the chance here to really acknowledge our partners in Italy. They did a fantastic job. Not only did they provide this digital subsystem, but we just shipped or carried on airplanes all of these shiny bits, and they put it all together and tested it to make sure it works. And they delivered it to the spacecraft facility in Toulouse, France, where JUICE was put together. And again, right now it's working great. And it's just another successful collaboration that we've had with this group in Italy that goes back, as I said, to the Mars radars and all the way back to the shuttle imaging radars. The antenna was provided by a contractor selected by the spacecraft contractor, which was Airbus, if you're familiar with them. Everybody's flown on an Airbus airplane. They also make spacecraft. And they found a vendor to make this antenna, which, again, it works great, but we had a few hiccups. Okay, just briefly, the science team. Here's a list. You don't need to read all the names, but you might recognize some of them. We have experts in radar sounding, in planetary science, and geology of these icy moons. All, or maybe it's not all, but just about everybody on here has some experience working on one of these other radars, whether it's Mars or whether it's the Europa Clipper's Reason radar, which I'll get to, RIME and Reason. Okay, by now you've probably figured that out. There's a little bit of a pun there. But you can see the institutions here, many from Italy, many from different institutions here in the US, and from several other countries as well. Okay, so I'm going to show a few examples from Mars of the radar data. So we'll start with Marsus. So it's kind of a blurry picture, but it actually holds a ton of information here. So this is the north polar cap of Mars, also known as the north polar layered deposits. And this is a topographic map, so red is high and blue and purple are low. The range of elevations here is about 3 or 4 kilometers. And you can see the horizontal scale. Now the vertical scale, again here, this is time, right? But we're able to do some tricks because we know where we should expect the surface echo to come from because we have the topographic map. And so we can say anything that comes later than that, let's pretend rather than it just going through free space that it's going through ice. And when we do that conversion from the speed of the wave in free space to the speed of the wave in ice, we convert time to depth, and look how beautifully the bottom of this ice cap comes into horizontal position. I'll show that once again, because I never get tired of this. I think it's just magic, the way this kind of twisty, curvy, messy thing becomes this beautiful straight line. And we were able to use data like this from Marsus. This is on Mars Express, another European Space Agency mission, to take an inventory to measure the amount of ice in both polar caps of Mars. It is by far the largest piece of the water inventory that we know of near the surface of Mars. If you melted the north and south polar ice caps of Mars and spread them all around the planet, it would make a layer about 20 meters deep. So there's a lot of water locked up in these polar regions, and we were able to quantify that using this technique. Yeah, so here I have the depth scale. You can see the thickest part here is about 2.5 kilometers. We made the cover of Science. Yay. This is from Mars Reconnaissance Orbiter, which is a NASA mission, but it carries the Italian radar Charade, which many of us in the US participated in. And here we did this super cool thing where we took the North Polar cap, a three-dimensional model, and we cut it like a cake. And then we put this, what's called a radargram, the radar image cross-section, on the inside of that cake. So that's what it looks like on the inside. So very cool. Definitely science cover worthy, I think. And this is part of a similar radargram over the North Pole. Again, here shown here. I don't have the topography scale, but you can see the lateral scale, and this is depth corrected. So this is the depth, and you can see the incredible detail now. Marsus was a very low frequency, so it, by the nature of how you process the signals at low frequencies, you cannot get as high resolution. Sharad was the shallow radar. It was intended to just look at the shallowest parts of Mars, and it was a higher frequency, and we were able to get some very nice, sharp resolution on all of these layers on the interior of the North Polar caps. And these are just some of the sort of interpretations. It wasn't instant that we discovered all of these things, but now in retrospect, this one image shows many different features. For example, when you see this sort of bend and curve here, that means these layers, which were deposited from the atmosphere, were being deposited on a sloping surface. It's not an indication of deformation or anything, because this ice really does not flow. In other places, we see these changes in the layer thickness. So some places were accumulating faster than others. We see these different packets of bright returns and darker returns. The brighter ones probably have a slightly more dust than their darker ones. All kinds of really interesting things that we learned about the interior of these ice caps from this radar sounding. So now let's take it to one of the icy moons of Jupiter and imagine seeing the interior. What's below of Europa? What's below all of those complex lineations and those floating icebergs and those fault zones? So it should be really, really interesting, because we have this capability on both RIME and Reason. So at the icy moons, RIME has this set of objectives. I won't go into much detail, because I've kind of touched on most of these, but we want to understand the ice shell. And we want to understand how, and if it continues, how it did in the past interact with the subsurface water. Because on JUICE we have a whole set of cameras, we'll be able to correlate what we see in the subsurface with the features on the surface at high resolution, and that will help us understand both how the objects on the surface formed, and seeing the surface objects will kind of guide us to places, interesting places where we might find something interesting in the subsurface. And we also want to understand what are the processes that are acting on these surfaces and subsurfaces. For Europa, similar. We're only flying by, if you remember, twice, but they're targeted at areas that seem to have been resurfaced recently. So we have the hope that maybe we can actually penetrate down to see the liquid water 10 kilometers or so deep, and maybe deeper. And also, if we do detect that boundary between the ice and the liquid, we can measure, therefore, the thickness of the ice crust. In Callisto, it's not likely we're going to see the liquid, but we can still explore the properties of its ice shell. We expect to get good penetration even in the Callisto ice, and try to understand the formation of its surface features. Just quickly, I won't go through all the numbers, but we have Marsus and Sharad at Mars, we have RIME, and then we have Reason, which I'll get to, at the icy moons. Reason's focused on Europa. And here are the frequencies. Now, again, using the Mars example, the low frequencies penetrate more deeply. The high frequencies give you high resolution in the shallow depths. We chose a center frequency of 9 megahertz, slightly lower than Sharad on Mars. Reason also has a very high frequency, VHF, 60 megahertz channel, and that will show all kinds of detail in the shallowest subsurface, maybe 500 meters to a kilometer down. The antennas, I'll talk about the antennas in a second. Marsus' antenna was 40 meters tip to tip. It's a whole other saga of how that deployment went, but it worked. And 40 meters is the largest radar antenna that we've ever put in space. These others are on the order of a few meters to 16 for RIME. Just quickly about reason. So as I said, reason has these 2 frequency bands. These long stick antennas here are the low frequency, and these little oval items here are the higher frequency, the 60 megahertz. And this is just to give you an idea of the low frequency and this orange wave. That's supposed to get perhaps as deep as the ocean, whereas the high frequency will look at the shallow features. Maybe there's some perched water in the shallower parts of the crust that will be detected by the higher frequency. And here's a list of the way that we've broken down the reason science measurements: sounding, altimetry, reflectometry, which means how does the radar reflect off of the surface from place to place. There are plasma effects that we'll be able to measure. Also ranging, in other words, the distance between the spacecraft and the surface, how does that change as Europa goes around Jupiter and interacts with the other moons? The ice shell of Europa is believed to kind of pump up and down under the varying influence of gravity, and that would change the distance to the surface in the spacecraft on different flybys of Europa. So we're going to see if we can try to measure that. That will help us understand the mechanical properties of the ice crust. Okay, I've touched on some of this, but I think people ask, because in all of this, I think the headline in the New York Times is when one of these things detects water below the surface, right? You've seen many headlines, scientists find water on Mars, right? Well, how many times has that happened, Bethany? Like 60, 80 times that scientists have discovered water on Mars. But actually detecting these subsurface oceans on one of these icy moons, that would be awesome. So is it possible? Could we do it? Well, we're going to try, but no promises, okay? For Ganymede, I think Ganymede is the focus of JUICE and RIME, but I think it's a bit of a long shot, because actually our best models say that ice shell is probably 100 kilometers thick or many tens of kilometers thick. It's difficult for the radar to get more than 10 or perhaps 20 kilometers before the signal just gets absorbed. So we wouldn't see that boundary. So I think it's a bit of a long shot. For Europa, both RIME and reason, especially at their lower frequencies, I think have a shot at seeing liquid water. Again, JUICE is only flying by twice, but reason will be flying by over 40 times. So many opportunities looking at many of the different regions on Europa. And that 9 megahertz band should penetrate 10 kilometers or more. And the most common number you'll hear for the average thickness of the Europa ice shell is 30 kilometers. We hope it's not that thick everywhere. Maybe there are thinner regions where we'll be able to reach the ocean. And there's this whole other idea that clearly water has reached the surface from time to time. There's some evidence that there are geysers actually leaking water, vapor out of, or droplets out of the crust of Europa. So the idea is that maybe there are some zones in the icy crust of Europa that have liquid water at much shallower depths. Those we would be able to see. Perched water zones, for example. For Callisto, in terms of liquid water, well, at Callisto we're going to be looking for other kinds of stuff. It'll be really interesting. It'll be great, I promise. But liquid water, that would be a big surprise. Okay, now a bit about the antenna. So here's the antenna in the spacecraft assembly facility in Toulouse, I believe. The arrow points to it. Here's a nice drawing of it. So when it's fully opened, it's 16 meters tip to tip. And so it's got these 2 4-segment sides that are each about 2 meters long, right? So you remember I counted 6 different deployments that it had to do. And those correspond to these hinges here on the parts that join those arms together. And so there are springs in those hinges that, oh my, sorry for the people online, you're not seeing me point, and I know I was supposed to describe in detail what I was pointing at, and I apologize. Okay, neither pointer works. I'll use this thing, and then people online can see it. So these brackets hold down these spring-loaded hinged elements. And so, for example, this one closest to us here, if the bracket is released here, this upper arm is going to jump out and swing out with the help of these springs, and then it's going to lock into place. And then the next bracket down below would be on, let's see, okay, so, yeah, so we start with this one, the next one down here, it would send those two arms now back the other way, et cetera, et cetera. So that was the idea, and seemed pretty reasonable, but 6 different events, and every single one of them had to work. So we did 2, the first 2, no problem, the top of each of these 2. So then we had a very short, stubby antenna, but we had 4 more events to go through. And so here is an animation of what happened after, well, before and after those first 2 pieces jumped out. So what are you looking at? Well, you're not seeing the whole antenna here, but if you count the number of arms here, you'll see that it jumps from 4 to 3. Okay, so the first 2 steps, 1, 2, you have 4, but that top one's gone now. Did you see that? Now there's just 3. And these were some different events where we tried to nudge the antenna up a little further to get it free. But after those first 2, one of these brackets stuck, and that's what we're looking at here. So now 1 arm is free and 3 more. The next one just did not go. It would not budge. And so the spacecraft team tried all kinds of clever things, like rotating the spacecraft to put it in the sun, and then rotating it away to get it cold, and warming it up and cooling it down again. They pulsed the engine of the spacecraft to give it a little shake or rattle. They said, oh, well, let's just deploy that big arm for the magnetometer. You saw that thing jump out of the jack-in-the-box. That's going to shake the spacecraft. They did that out of sequence because we were supposed to be done by then before they did that. And that, sure enough, that rattled it, but it never did free it up. Finally, it was kind of the last chance we had, which was open the other side, the unstuck side, all the way. And since they share this bracket, this mounting thing, hopefully that will shake it enough. There was just a little pin that was in the way holding down a clamp. And if that pin just moved, it was literally millimeters, and it worked. And so that's what you see here in this one. You see it, boom. Okay, so start again. At the start here, you see 3 of the arms. We had released the other 2 latches, and so there it goes. The top 2 arms, they just went shooting out, and you can see they're way over there to the right. You see it kind of going waka waka, settling down after it's finally done. So in the end, success. I had many sleepless nights. It was a bit of a nightmare, and it was kind of deja vu because something similar happened on Mars Express with Marsus, but that one got deployed. So we're on our way. We've turned the radar on. We've listened for noise. There's some noise. Unfortunately, the spacecraft is a bit of a noisy beast, but we turned the transmitter on. Everything is working beautifully. Once we get to a target, and we're hoping that in a year, when we fly by the moon and the Earth, we can turn on the radar and get some echoes off of the moon, because that's a great target for a radar. So that'll be the first time we actually get echoes, we think. Okay, so to sum up, JUICE is on its way to Jupiter. We'll arrive, well, it's not going to be that long, 2031. After flying by the 3 moons many times, it'll go into orbit around Ganymede, and that will be a spacecraft exploration first. Many instruments, including RIME, and RIME will probe the icy crusts of the moons. And around the same time, Clipper, which has not launched yet, it'll launch next year, will arrive at the Jovian system, and will start flying by Europa time after time. And so sometime in the 2030s, we hope to answer this question, among many others. Are these icy moons habitable, or even today inhabited? So thank you very much, and I'm available for questions.